Hello, everyone. We are very glad to present our work, X-Check GPU-accelerated design rule checking via parallel Sweepline algorithms. I'm the speaker, Zhuolun, from the Chinese University of Hong Kong. My presentation today mainly consists of several parts, including the background motivation of our work, and then the parallel algorithms for design rule checking, as well as some discussions for GPU implementation. Finally, I'm going to demonstrate some experimental results. Design rule checking is a very crucial stage in physical verification. For the manufacturability of the circuits, the manufacturer has come up with a set of geometric constraints known as design rules. And design rule checking is going to ensure that the layout does not violate this set of geometric constraints. The figures here demonstrate some typical rules. At the left-hand side, we have some width and spacing rules in the metal layer. That is, we have some minimum width requirements of the components, as well as the minimum spacing requirements between two components. Similarly, at the right-hand side, we have some inclusion rule. That is the minimum inclusion distance between a metal layer and a via layer. And there are several reasons for us to consider GPU acceleration for design rule checking. Firstly, we have seen the explosion in the number of design rules in advanced technology nodes. And it has been pointed out that many classic parallel algorithms, including the data parallelism as well as the task parallelism, do not scale beyond a few CPU cores. And recently, GPUs have demonstrated a great potential in EDA tool acceleration. We have observed two popular methodologies to develop efficient GPU-enabled EDA tools. The first one is to cast a design automation problem into another problem solvable by current tools and infrastructures. For example, DreamPlace casted the analytical placement problem into neural network training so that the current deep learning toolkits can be used to develop efficient analytical placement. And similarly, if we consider a netlist as a graph, we can use the graph manipulation tools to deal with gate level simulation. And FastGR considers the patch net routing ordering problem, which is solved by task scheduling engines. And with the current infrastructures, researchers can focus more on the problem formulation and customization and do not have to build everything from scratch. And the second methodology is to design novel GPU-friendly computation kernels for some critical tasks in the design flow. Examples we have seen include the placement, maze routing, and the STA stages. And our work is closer to the second methodology here. And then we are going to describe our problem. And here is the informal description. And a layout is can be considered as a set of axis parallel polygons. And the distance rule says the following: any two edges must not be closer than a predefined minimum distance. That is, we have the minimum distance requirement of these edges. And the distance violation is a pair of edges in the layout that violate this distance rule. Given the layout, our task is going to report all the distance violations within this layout. Say we only consider horizontal edges. Given a set of horizontal segments in the 2D plane, we are going to report the segment pairs from this set, whose horizontal projection is non-empty and vertical distance is smaller than the predefined delta. Again, we have a set of horizontal segments, and we are going to report the segment pairs where they have some overlap in the x ranges and their vertical distance is smaller than delta. Actually, we have an efficient algorithm to solve the distance check problem in the sequential setting, which is known as the Sweepline algorithm. A Sweepline algorithm can be considered as moving a virtual scan line from left to right and process all the events it encounters. So firstly, we are going to sort all the segment endpoints by assigning x coordinates. And we are going to use a binary search tree to maintain all these endpoints, specifically their y coordinates. And then we are going to scan all these endpoints from left to right. And whenever we encounter the left endpoint of a segment, we are going to do a range query in this binary search tree. And we are going to report the corresponding segment pairs because they are all violations. And finally, we are going to insert this segment into the binary search tree. And otherwise, if we encounter the right endpoint of the segment, we are going to delete this segment from the binary search tree. In this way, actually, the binary search tree maintains a set of so-called active segments. And the complexity of this algorithm is big O of n log n plus k, where n is the number of segments or endpoints, and the k is the number of violations. This is output sensitive. Actually, this complexity is optimal because we have an element uniqueness problem reducible to our problem. And this element uniqueness problem is lower bounded by big omega of n log n. And also we need the big omega of k time to report all these violations. And then we are going to consider the parallel algorithm, which is a parallel vertical sweeping algorithm for our distance check problem. Here we provide another view of Sweepline, that is the prefix sum problem. Say we have an array of numbers, and we are going to compute the prefix sums. This is similar to Sweepline as it scans these numbers from left to right, and then sum up all these elements all the way to the end of this array. So consider doing it in parallel. Here we provide an interesting way to do this. Suppose we have 9 numbers and we are going to have 3 threads. Our approach consists of 3 steps. The first step is batching. In this step, this 9 numbers is divided into 3 blocks. And for each block, we use the thread to compute the sum of the consecutive elements in this block. So after the first stage, we have this 12, 13, and 2, which is sum of each block. And the second step is sweeping. We are going to sweep from left to right to sum up these partial sums. So after this sweeping, we have 12, 25, and 27 at their corresponding positions. Notice that these are the final answer for these positions. And the remaining thing to do is to refine all the other prefix sums. And we are going to use the partial results at the second step to refine all the other prefix sums. And notice that this can be done in parallel within each block. And we are going to use this strategy to do vertical sweeping of our distance check problem. The key idea here is the prefix structure actually contains a set of segments that are below current segment within delta in the y direction. So we are going to construct these prefix sums for each segment using our parallel sweeping algorithm. Because this prefix structure actually deals with the y direction, we remain to check if each pair of segments within the prefix structure overlap in the x direction. If they overlap in the x direction, they are actually the violations we are going to report. We also come up with the complexity analysis of this strategy. So basically, we are going to analyze the complexity of each step. And this also relates to the distribution of these segments because it affects the prefix structure of each segment. So at the worst case of all the possible distributions, say we have roots n of processors, the depth of this algorithm would be roughly big O of roots n plus some logarithmic factors. And we argue that it provides some insights to design parallel algorithms because we prefer to decompose the problem by the simple direction for possible parallelism and leave the complex work to each individual processor. So the emphasis here is quite different from the sequential version because in the sequential version, we will use the Zhuolun algorithm to deal with the hard direction and maintain the easy direction for efficient query in the binary search tree. Especially in our distance check case, the horizontal direction is a hard direction because we'll have 2 endpoints for each segment. Therefore, we do not have a total order of these segments. The figures here also illustrates our insights. So the left-hand side is a sequential version where the complex decomposition, the x direction is performed by the Sweepline algorithm. And the y direction is going to ensure the very efficient query in the binary search tree. So we will leave it for our data structure. However, in the right-hand side is the parallel version. We are going to decompose the problem from the simple direction for possible parallelism. and we are going to parallelize all the prefix structure construction. And the complex decomposition is left for each kernel. So these are also done in parallel within the kernels. And then we are going to discuss some implementation details. The Zhuolun algorithm itself is actually very GPU friendly because it is a divide and conquer framework. And we use some common strategies, including dynamic algorithm selection, where we are not going to invoke GPU if the problem size is small enough. And we'll consider different kernel granularity. We can assign threads per tile-wise and polygon-wise for per prefix structure or for each check. We can do parallelism in different granularities. And we also discuss a bit about sorting, because there are two commonly used parallelizable sorting algorithms on GPU. One is the merge sort, which is a comparison-based sorting algorithm. So whenever you pass the comparison function object as an argument to, say, first sort, it launches the merge sort. And another sorting algorithm is radix sort, which is not comparison-based. It mainly works for numeric data types, for example, the built-in integer and the default comparators. Say here we want to sort an array of struct S, and we will sort these structs according to the key field. And here n is the length of the array. Here we provide another way we call copy, sort, and permute to sort these structures. The idea is straightforward. Firstly, we are going to copy all the keys out, as well as their indices, into separate arrays. And then we are going to sort these keys because there are some built-in numeric types. We are going to sort these keys as well as their indices. And finally, we are going to permute our original array according to the sorting result. Therefore, we call this strategy copy, sort, and permute. And intuitively, it involves more things to do so that it should be only used with large arrays. And here the runtime comparison between three strategies, including the thrust sort, our copy, sort, permute, and a mix of them. So we see that in all of the test cases we have, the mix strategy actually outperforms. And we also perform an synthetic experiment. So we can see that at the array length of around 10,000, the copy, sort, permute outperforms merge sort. So this confirms our intuition that we only have to use copy, sort, permute for large arrays here. And then we are going to perform to demonstrate the experimental results. And our algorithms are implemented in C++ and CUDA for GPU program. And the algorithms are integrated into the K-layout engine, and the baseline is also a K-layout design rule checking engine with the multi-threaded settings. And all the test cases we use are synthesized from the Open Road project. And here are the environments of our experiments. And the first table shows the statistics of the benchmarks and results of the width check. So we have 4 different circuit designs with different sizes, different number of polygons and different edges. And width check is the most simple task because it only involves the distance check within each polygon. So in this cases, K-layout runs already very fast, and we observe some mild speed up in the 2 big cases. And the second table is for enclosing check and space check. So for these 2 checks, the CPU version runs rather slow. So we observe some significant speed up using our algorithms. For enclosing check, X-check achieves up to 1,200 times speed up, and with an average of more than 61%, 61 times speed up. And for space check, we have an average of 45 times speed up. This is very significant. And we also care about the runtime breakdown. And firstly, we are going to see for the width check, And here, each horizontal bar is for one GPU thread. And the purple and gold portions are for the merge stage and the check stage. Note that we mainly accelerate the check stage here. So the left figure is for the K layout and the right figure is for S check. You see that after GPU acceleration, the merge stage takes a much larger portions, and it illustrates the limited speed up we can achieve, as well as showing that this merge stage becomes the new bottleneck. And this is for the enclosing check, and similarly, each horizontal bar here is for one GPU thread. And the purple portion is for the merge stage, the gold portion is for the sorting stage, the blue for previous build, and orange for the violation report. We can see that for many threads, the merge stage takes up most of the time. So it is the new bottleneck after GPU acceleration for the rest checking stage. And here is our conclusion. We have presented a parallel Sweepline algorithm for design rule checking and also discussed some GPU implementation considerations. We have integrated our algorithms into an end-to-end flow and have demonstrated significant speedups. And the future work includes a parallelization or the acceleration of the merge stage as it becomes the new runtime bottleneck. And we feel that it is desired to develop more GPU programming infrastructures, including associative data structures and their thread-safe solutions. Thank you.